So in today's video, we're going to go ahead and start applying these different concepts that we've been covering in previous videos, including concavity, the second derivative test, and of course points of inflection, stationary points, everything, in order to actually sketch a curve. And so what we're going to do here is we have this curve, which is x cubed plus 3x squared, right? It's just a polynomial. And we're going to see how we can actually use the first and second derivative, how we can apply these concepts that we've learned involving the first and second derivative of this function in order to actually sketch the curve in a relatively accurate manner. And so let's go ahead and do that. So this curve is relatively simple compared to some other ones you may see, but I just want to give you a basic example so that we can kind of understand what the general approach would be when we're curve sketching using calculus. And so the first thing we can do is we can go ahead and take the first derivative of this function, right? Because we want to just see where we have any stationary points in order to determine the relative extrema. And so the first derivative is going to be 3x squared plus 6x, right? And then if we're going to go ahead and set this equal to 0, because we know it's never going to be undefined, it's a polynomial, so we just have to look, when we're looking for stationary points, in this case we're just looking for points at which the first derivative is equal to 0. Then we can go ahead and factor out the 3x. So let me do that. We have the 3x times x plus 2 is equal to 0. And this tells us that either x is equal to -2 or x is equal to 0. And so these right over here, these would be our critical points, or our stationary points, right? And so now we know that we have two stationary points. What we can do is we can go ahead and draw our little number line out in order to determine the nature of these critical points. Let me draw our number line, and let me mark the 2 points. We have -2, and here we have 0. And so let's go ahead and look at f prime of x, or the sign of f prime of x, for values that are less than -2, so within this region over here. If we were to pick some arbitrary value, let's say -3, we can take f prime of -3, which will be -9 times -1, which is equal to +9. And so we're going to be positive over this interval, or f prime is going to be positive, and so that tells us that f is going to be increasing over this interval. And then for values from -2 to 0, we can go ahead and take some arbitrary number. We can take maybe f prime of -1, and so that will be equal to -3 times +1, which is equal to -3. And so we're going to be negative over this interval. And so that tells us that f is going to be decreasing because f prime is negative. And then finally, we can take a look at values that are greater than 0. And so we can take maybe f prime of +1 would be pretty easy. So f prime of 1 is going to be 3 times 3, which is +9. And so f prime is positive, which tells us that f is increasing over this interval. And so now we're able to determine the nature of these critical points. So -2, we're increasing, right? And then we reach -2, we're stationary, and then we start to decrease after that. So we can say, right over here, we can determine that at -2, we're going to have a relative maximum, right? If you recall from the first derivative test. And then at 0, we're decreasing, we hit 0, we're stationary at 0, and then we start to increase again. And so that tells us that at 0, we're going to have a relative minimum. And so now we already know the maximum and minimum values, or the relative extrema of this function, just using the first derivative. We haven't even delved into the second derivative yet. And so for the second derivative, what we're going to do is we're going to try to find the points of inflection, right? Because we want to see where this curve changes concavity. And so in order to do that, we actually have to find the zeros of the second derivative, or where it's undefined, and then see where it changes signs from either positive to negative or negative to positive. And so let me take the second derivative. There's a very loud truck passing by for some particular reason. So f double prime of x, if we go back to f prime of x, that's going to be 6x plus 6. And again, if you don't really understand how I got that, then I encourage you to review the basic rules of derivatives. So 6x plus 6 is going to be our second derivative. And we know that this is going to be defined. Again, this is just a linear function, so it's going to be defined for all real numbers. So when we're looking at inflection points, or points of inflection, or at least candidates for inflection points, we just need to find the points at which f double prime is equal to 0. And so then we get 6x is equal to -6, which tells us that x is equal to -1. And so this may be a point of inflection. So this may be a point of inflection. And the reason I say may is because we need to determine whether f double prime changes signs at this point. So let me go ahead and draw in another very small number line over here. Let me mark our candidate for our inflection point. Let's take a look at values that are less than -1. So we can take, for example, f double prime of, let's say, -2. Let me write f double prime in factored form. So that's going to be 6 times -2 plus 1, which is going to be -1. So that's going to be equal to -6. So we're negative over this interval. And then for values that are greater than -1, we can pick, for example, f double prime of 0. That's going to be equal to 6. And so we know that we're going to be positive over this interval. And so that tells us that this is going to be a point of inflection, right? Because we change signs from negative to positive, or f double prime changes signs from negative to positive. And so that tells us that at x equals -1, we do have a point of inflection. We do change concavity. And so now we have all of the information that we need. For the most part, we could find the zeros of the function if you want to be very particular. And actually, it's pretty easy for this one. Let's go ahead and do that. So x cubed plus 3x squared is equal to 0. You can just factor out an x squared times x plus 3 is equal to 0. And that tells us that the zeros of this function are going to occur at x equals -3 or x equals 0. And here we are going to have a double root or a double zero, whatever you want to call it, because we know that this x squared term, that's what the x squared term tells us. And so now we actually have every piece of information we need to sketch this curve. And so let's go ahead and actually do that. I'm going to change colors because we've been using one color throughout this entire video. This is a nice blue. I think that will look good. Okay. So first of all, let's go ahead and mark all of the crucial points that we know. So we know that we're going to have this point right over here at -1. We have another important point at -2. At -3, we're going to have a 0. And of course, we have our origin. And what we can do now is, if we want to be even more accurate, we can find the value of the function at these different points. So really at -2 and -1, because otherwise we're going to have zeros at -3 and x equals 0. And so let's go ahead and try to find f of -2, which, let me scroll up over here to actually remind myself of the function. It's going to be -8 plus 3 times 4, so that's going to be 12 minus 8, which is equal to +4. And then f of -1 is going to be, it's going to be -1 plus 3, which is going to be +2, right? And so now we have these points. We have the point -2, 4, and -1, 2. And so now we are actually ready to graph. I know I said that multiple times, but now we have truly everything that we need. So let me go ahead and scale our axis over here. This isn't extremely accurate, but it's all right. So this will be 2, this will be 4. And so now we can go ahead and start sketching this curve. So we know that we're going to have a 0 at x equals -3, right? And then at x equals -2, we're going to have a relative maximum. And we know that this is going to occur at the point -2, 4, right? That's why we found the value of the function. Let me make sure that that's accurate, okay? And then we're going to have a point of inflection at -1, 2, right? So over here, we're going to change concavity and start, we're going to change concavity from a concave down, because we're negative, to a concave up, because then f double prime becomes positive. And so we have that at x equals -1. And then here we're going to have a 0 at the origin, and then we're going to start increasing again. And so let's go ahead and try sketching that in. So we know that we're going to be decreasing all the way over here. We'll hit x equals -3, we'll have a 0, and then we can continue to increase, and then we'll reach our stationary point over here at x equals -2. And then we hit our stationary point and we start to kind of decrease, and then we change concavity over here at x equals -1. And as we change concavity, we reach our 0 at the origin. And again, we begin to increase, and then we don't really care what happens after that. We can just draw an arrow because nothing too interesting will occur after that. Let me just try to smooth this curve out a little bit. And that would be what our function will look like. And if you actually look up a graph of this function, then it will look essentially like this. This is just not a very accurate sketch, but it is close enough. And we have all of the crucial points marked out. And if this was perhaps an IB or an AP exam question where they ask you to sketch a function using calculus, then this would be a very valid sketch that would award all the points. And so essentially, we can use this for many more different functions, many much more advanced functions. I just wanted to use one with very simple and nice numbers so we get the idea of the process.